In this video we're going to talk about 6.5, which is our double and half angle formulas. We just finished up with our sum and difference formulas. So again, we're going to kind of use what we know about that and apply that a little bit further here in terms of sum and difference. But we're going to use sum and difference, but we're just going to use it in terms of adding the same angle to itself. So again, if you ever forget these double angle formulas, you can always just kind of use your sum formulas for sine, cosine, tangent, and then just kind of do it to itself or at the same angle. So if I look at the very first function here, sine of 2 alpha is really the sine of alpha plus alpha. So remember, if I use my sine sum formula, I have the sine of alpha times the cosine of alpha plus the cosine of alpha, which is the first angle, times the sine of alpha. Since the angles are the same here, I can kind of rewrite this product as the sine of alpha times the cosine of alpha, and then that gives me 2 sine alpha cosine alphas. So when I do the double angle formula for sine, it's really equal to 2 times the sine of alpha times the cosine of alpha. Here I'm doing the cosine of 2 alpha, and again I'm going to use that sum formula, or that sum formula process. So cosine of alpha times cosine of alpha minus the sine of alpha times the sine of alpha. So when I multiply a trig function by itself to the same angle, it's kind of like cosine squared of alpha minus the sine squared of alpha, which kind of looks like the Pythagorean identity, which was sine squared of alpha plus cosine squared of alpha, but it is a difference. And remember that commutative property doesn't exist with differences. So another way to kind of rewrite this is using that trig identity of sine of alpha plus cosine of alpha squared equals 1. And when I kind of solve this for sine squared of alpha, I subtract cosine. So sine squared of alpha really could be equal to 1 minus the cosine squared of alpha. So I want you guys to be aware that if I would go ahead and plug this function in for sine squared, this also could be equal to the cosine squared of alpha minus 1 minus cosine squared alpha, which when I distribute a negative and then combine like terms, it's really equal to 2 cosine squared alpha minus 1. And in the same respect, if I would solve for cosine squared and distribute the other way, that would also be equal to 1 minus 2 sine squared alpha. So some textbooks and some problems don't just show my double angle is cosine squared minus sine squared. They also do this 2 cosine squared minus 1 and 1 minus 2 sine squared with the same angle. So those are all 3 different of the same form. So this is equal to this, which is equal to this. All of these are double angle formulas for cosine. And then tangent of alpha, again, just using that same sum formula, have the tangent of alpha plus the tangent of alpha all over 1 minus tangent of alpha times tangent of alpha squared. So I'm just going to square that, make that a little easier for myself. So then when I just combine my terms here, I get 2 tangent of alpha over 1 minus tangent squared alpha. So this is my double angle formula for tangent. I don't actually go ahead and memorize these guys. All I do is I remember how to do it with the sine, cosine, and tangent sum formulas, and kind of can refine those. Alright, so let's go ahead and try some practice problems here. What they want me to do here is find the sine, cosine, and tangent of the double angles, so cosine, sine, and tangent of 2u. They tell me something about tangent of u as that being negative 15 over 8, and they also tell me u is between pi over 2 and pi. So they tell me that this angle u has to be in the second quadrant. So what I'm going to do then is I'm going to go ahead and try to find the different trig function values of u in that double angle formula. So the first thing I might want to do is go ahead and use the tangent of u that I have and draw a triangle in the second quadrant. And that's going to be opposite over opposite over adjacent. However, I'm going to make my x value negative and my y value positive since I'm in the second quadrant. Using my Pythagorean triples, 8, 15, 17 is going to be my other side there of that right triangle. And then what I want to try to find is I want to try to find the sine. I want to try to find the sine of 2u. To do that, I'm going to use my double angle formula for sine, which I know is 2 sine of u times cosine of u. Sine of u would be opposite over hypotenuse, so that would be 2 and then times 15 over 17. And then cosine of u would be adjacent over hypotenuse, that would be negative 8 over 17. When I multiply these and combine like terms, what I end up with is a negative 240 all over 289. And just looking at the factors here of my denominator, 17, 17, here I have a 3 2's, a fourth 2, and a 15, 3 and 5. None of these terms are going to have like terms to cancel out, so I'm just going to leave that fraction the way it is. And again, using this information, I can kind of help myself find the other parts. Remember here, if I'm trying to find the other function values, I could use my double angle formulas for cosine and tangent. However, these two sides automatically form a third side of my triangle, my double angle for 2u. So when I look at another triangle here, I don't really care which I don't know which quadrant it's in, because I can't really tell based on that u value. So what I'm going to have to do is I'm going to have to use my double angle formula one more time, and then hopefully then that will help me find this is my opposite side of that triangle, this is the hypotenuse. I need to find the adjacent side, and then obviously once I find adjacent hypotenuse, adjacent and opposite, then I can find tangent. So if I want to find the cosine of 2u, then I'm going to go ahead and pick one of my trig functions. It doesn't matter which one I pick. Sine is positive, so maybe I'd go ahead and just use that 1 minus 2 sine squared of u. So that's 1 minus 2 times sine of u, which I know is 15 over 17 squared. When I simplify this, I'm going to end up with a 1 minus 2 times 15 squared is 225 all over 289. And when I take away 1 from 450 over 289, I end up with a negative, because 450 over 289 is bigger than 1, a negative 161 over 289. So I found cosine, I found sine. The only thing I'm missing here is tangent. And remember, tangent is going to be of 2u, is going to be opposite over adjacent. So the opposite side would be negative 240. And the adjacent side would be negative 161. So it looks like I'm down in the third quadrant for this angle, since both the sine and cosine are negative. And since sine and cosine are both negative, then I know the tangent has to be positive. So this is going to be 240 over 161. And I can leave my answer like that. If I like, that's fine. So here I found the sine, cosine, and tangent of 2u. Here I want to find the exact values of the sine of 60 degrees using the double angle formula. I know how to find the sine of 60 degrees already. That's pretty easy because it's on my unit circle. When I'm standing at 60 degrees, sine is going to be root 3 over 2. However, they want me to use the double angle formula. So I need to figure out a way to either double or kind of what number could I double to get 60, if that makes sense. That's the question I'm asking myself. What number could I double to get 60? So when I look at sine, I'm going to have the sine of 2 times 30 degrees is going to end up with 60. And remember, the sine formula for the double formula is 2 times the sine of that angle 30 times the cosine of that angle 30. And then when I plug this in, obviously sine of 30 is going to have a y value of 1/2 and an x value of cosine of 30 is going to be root 3 over 2. So this is going to be 2 times 1/2 times root 3 over 2. So I end up with a 2 root 3 over 4 But again, 2's cancel, so I end up with just a root 3 over 2, and that's exactly what I should get for that answer. Let's go ahead and look at example 3 now, on the next page. Example 3, find the exact value of the cosine of 2 times the tangent inverse of negative 4 over 3. Remember, tangent inverses are just tangent trig inverses of angles. So tangent inverse of negative 4 over 3 is really just an angle, theta. So in my head, I'm going to draw a picture here. Down, obviously, tangent's negative, so I'm down in the 4th quadrant for that inverse. And then I want to go ahead and label its sides, opposite and adjacent. 3, 4, 5 are my 3 sides of my Pythagorean triple. This is really the cosine of 2 times some angle theta. So this is really just a giant theta. Remember, my cosine double angle is like cosine squared of theta minus a sine squared of theta. Once I have those memorized. Cosine is adjacent over hypotenuse, so 3 over 5 squared minus negative 4 over 5 squared. Squaring a negative is going to make it positive, but again, I'm going to subtract it. So here I'm going to have 9 25ths minus 16 25ths, which is going to end up with a difference of negative 7 over 25. Again, if you ever feel like you're picking this up pretty quickly, go ahead and pause the video and jump ahead, and then go ahead and rewatch the video to make sure you understand or you picked up on it. We're going to verify an identity algebraically. So when we verify here, we're going to kind of draw our line and look at this function to clarify. If you ever have a graphic calculator, always go ahead and graph both sides in y1 and y2 and make sure that that works. That kind of gives you an idea to see if this is the same thing. So the cosecant of 2 theta is like cosecant over 2 cosine theta. What I might want to do is use the left-hand side and see if I can get 2 thetas or my double angles into regular angles. I know how to do that using my double angle formulas. So the first thing I might do with cosecant is actually use its reciprocal function, which would be 1 over the sine of 2 theta. And then once I reciprocate it, I know sine of 2 theta, and that has to be equal to its double angle formula. So 1 over 2 sine of theta times cosine of theta. Looking at this function, it doesn't look like I'm quite there yet, but it's not that far from being finished. I might move up here to get more space. If I have this really 1/2, I can kind of pull him out to the front, and I have a 1 over sine of theta if I break this fraction up times a 1 over cosine of theta. And once I break it up, I might realize, oh, I can actually take that 1 over sine and I can reciprocate him back to a cosecant. So when I do that, I end up with a cosecant up in the numerator, all over a 2 times cosine in my denominator. I'm not going to reciprocate the cosine because, well, the other side of my proof isn't reciprocated, and that's how I want it. So, yeah, verified, done. All right. So, moving forward here, those are our double angles. Here's our half angles. So when I have the sine of a half angle, again, these are just a little bit more work. You might have to memorize these, but when you're keeping this in mind, just make sure that you're following which quadrant my angle is in. That's the big thing. We always make a mistake here. The sine of u over 2 and the cosine of u over 2, depending on the quadrant in which u over 2 lies. So even though I'm switching back to u, I have to make sure I understand where u over 2 is located in my half angle formulas. So here I have the cosine of 15 degrees, which is not on my unit circle, but is there some angle on my unit circle which I could go ahead and cut it in half to get 15? Well, that would be the cosine of 30 over 2, or 30 divided by 2. So when I use my half angle formulas, I have to use the, because this is plus minus, the sine, plus minus sine is going to depend on which quadrant my original angle is in. 15 degrees is located in the first quadrant. So I'm going to go ahead and make sure in first quadrant cosine is positive. So I know it's going to be a positive square root of 1 plus the cosine of 30 degrees all over 2. So cosine of 30, that's equal to root 3 over 2 all over 2. What I might do in simplifying this process, I want to add 2 numbers. This is really just like 2 over 2. If I change 1 into 2 over 2, then I end up with a I end up with a 2 plus root 3 all over 2, all divided by 2. But again, dividing by 2 is like multiplying by the reciprocal. So really I end up with something that looks like 2 plus root 3 all over 4. And when I square root the top and bottom, I end up with a positive square root of 2 plus the square root of 3 all over 2. If simplifying possible, always kind of try to get back to a monomial denominator in an integer form. That kind of makes it nice and easy to find. We only have 2 more examples to try here. Example 6 with our half angle formula. They want us to find the exact value of sine of 75 degrees. Remember, we did this back in section 6.4 in one of our examples. So again, when we go back, check to see if the answers are the same. We want to take an angle, we want to cut it in half to get 75. Well, to do that, if I multiply 75 by 2, I end up with 150 degrees. So the sine of 150 over 2 is the angle that I'm trying to find. 75, remember, is in the first quadrant, right? 75 degrees, that's between 0 and 90. However, 150 is in the second quadrant. So when I'm going through and I'm looking at the different positive or negative, remember, it's always about the original u over 2 where he is located. So since 30 in the previous problem, was also in the first quadrant, now here I'm going to look at where 150 is located. Sine in 150 in second quadrant is also positive, so this is going to remain positive. Square root of 1 minus the cosine of 150 degrees all over 2. So when I simplify that, I get 1 minus a negative root 3 over 2 for cosine of 150 all over 2, so that's really just plus. So I end up with a 2 plus the square root of 3 all over a positive 2 when I simplify that process like we did in the last example. Alright, we do have one more example here at the bottom. See if you can try that on your own, and we'll go over it next class as a group. There's also homework at the bottom. It's been updated, so don't look at this right here, but make sure you check the bottom of your notes and try those homework problems as well.